We also looked at relative refractive index and then reverse or inverse refractive index. What is absolute refractive index of a material? A kind of revision. What is the absolute refractive index of a material? Frida, can you free us? What do we mean by the absolute refractive index of a material, Frida? Please, let's not waste time with our responses. Frida, are you there? Hey, anybody else? Anybody else to share with us what absolute refractive index is? Okay, so the absolute refractive index of a material is the refractive index of a material, or the real or the actual refractive index of a material when light moves from air into the material. Okay, so the absolute refractive index is the real refractive index of a material when light moves from air into the material. And so we say that the absolute refractive index of a material is the actual or the real refractive index of the material. So when light moves from air to glass, or air to water, okay, and we want to determine the refractive index using Snell's law. This is angle of incidence I, because the light. Okay, Frida, it's noticed. Because from the light is moving from air to glass, it will bend towards the normal. So this becomes the angle of refraction. Okay, so determining the refractive index as light moves from air to glass. Let me use the refractive index as light moves from air to glass is equal to Snell's law, which is sine I on sine R. This is what we term as the absolute or real refractive index of the material. Now, what we mean by refractive index is that the refractive index of a material is the measure of the ability of the material to deviate or bend light. The measure of the ability of a material to bend light is the refractive index of a material. So the absolute refractive index of glass, for instance, is 1.5. What this means is that glass can bend light 1.5 times as can be done by air. Glass can bend light 1.5 times as can be done by air. And then the absolute refractive index of water is equal to 1.33. What this statement means is that water can bend light 1.33 times as can be done by air. Okay, so that is what we mean by the absolute refractive index of a material. Then inverse refractive index. With inverse refractive index, we are recapping from what we discussed last time. With inverse, okay, before we discuss inverse, The absolute refractive index of a material is given by Snell's law, which is the ratio of the sine of the angle of incidence to the sine of the angle of refraction. This is also equal to the ratio of the speed of light in air to the speed of light in a medium. And the same absolute refractive index of a material can also be determined by the wavelength of light in air over wavelength of light in a medium. So these are different relations or formula that can be used to calculate for absolute refractive index. This has to do with change in direction as light moves from one medium into another. This has to do with change in speed as light moves from air, okay, to another medium. This is change in wavelength as light moves from air into a medium. So these are different expressions that can be used to calculate for absolute refractive index. Okay. Then reverse refractive index. Reverse refractive index. Look at this situation. We are moving from air to glass. Now, when we reverse the path, to this time move from glass to air. So if the path is being taken in this manner, before it was from air to glass, now we are reversing the path. So when you take the refractive index as light moves from glass to air, this is equal to sine of R over sine of. This is what we call as the reverse refractive index. And we went through this last time. Then we derived an equation which says that the product of the absolute refractive index of a material from air to glass and the reverse refractive index from glass to air, this product is always equal to 1. Okay, so whenever you have two media, okay, here are two different media has to do with air and glass. Assuming we have the refractive index as light moves from 1 to 2. When we multiply the reverse refractive index 2 to 1, this product must always give us 1. Very, very important equation we'll be using as we move on. Then we also spoke about relative refractive index. With relative refractive index, we are comparing. In physics, the word relative means a state of comparison. So we are comparing the refractive index of two different media. Comparing the refractive index of two different media. So if we have water and then glass sandwiched together, and light, that's the normal, light moves from one of them here, from light is moving from water to glass. Please, if light is propagated from water to glass, how will the light bend at the boundary? How will it bend? Will it bend away from the normal or towards the normal? Yes, anybody to help? If light moves from water to glass, how will the light bend at the boundary between the two media? Will it bend towards the normal or away from the normal? Please, anybody can answer.
Say away.
Luther, come again. Will it be away or towards the normal? And there can be a different view as well. If you have a contrary view, you can share with us. Will it be away or towards the normal? Luther, after communication, please mute yourself, okay? After answering, quickly mute yourself so we can. Mamiya, will it be away if light is moving from water to glass? Will it deviate towards or away from the normal? Mamiya.
Glass. If the glass is light, it will deviate away from the normal.
Mamiya, any type or kind of glass is denser than water.
Water.
Yeah. So how will it deviate?
Towards the normal.
Any kind of glass, of course, is denser than water. So if the light will be deviated towards the normal. So if this is the angle of incidence, this is the angle of refraction. Therefore, when you take the refractive index as light moves from water to glass, it is equal to the absolute refractive index of glass, the ratio of the absolute refractive index of glass to the absolute refractive index of water. This is what we mean by relative refractive index. Okay, this is what we mean by relative refractive index. And then, so we went through this in our last meeting. Today we are going to look at refraction of light in rectangular and triangular prism. And this is, I have in my hand a rectangular prism, even though part of it is broken, but it still can serve a very good purpose. So this is a rectangular prism. It has a rectangular shape. The other one is a triangular prism. We use this too for light experiment in physics. So right after vacation or when school actually reopens, in fact, you'll be experimenting so much on these two and then on lenses. So we'll begin with refraction of light in rectangular prism. Then if we are able to finish, we go through triangular prism. Okay. Now prisms refract or bend light. They bend or refract or deviate. Okay, all the adjectives can be used. They bend, refract, they deviate. Optics. Light is broad, so we would quickly go through the important areas which would, help in your practicals and then WASI. Then we will switch to other topics as well. So, refraction of light, refraction of light in a rectangular prism. Rectangular prism. So the prism I showed you has a rectangular shape. So let's draw the outline of the prism. This is actually used to verify Snell's law. So A, B, C, D are parts of the prism. Okay. Now, let's draw a normal because we are going to incident light at one end. So a normal drawn through. The normal is always perpendicular to the surface. So let's incident light at one end of it. This angle is the angle of incidence. Now, once the light is moving from air to glass, how will the light deviate? Yes. Once the light is being propagated from air to glass, how will it bend? Yes. Anybody, quick one. Quick observation. The light is moving from air to glass. How will it bend? Luther, Mami ya, Mami Fusua, Kelvin. How will the light bend?
It will bend to the normal.
Good. Because glass is denser than air and the light is moving from air to glass, it will bend towards the normal. So this becomes the refracted ray. The ray isn't bending so much. Let me bend it proper. Now, when the light is coming out of the prism, because this time around, its path is from glass back to air, then it will deviate away from the normal. So this is the incident ray. This becomes the refracted ray, and we call this as a emergent ray. The angle from the normal to the incident ray is the angle of incidence represented by I. The angle from the normal to the refracted ray is the angle of refraction R. Then the angle from the normal to the emergent ray is the angle of emergence, E. So where I equals angle of incidence, R, angle of refraction, E, angle of emergence. Okay. Now there is another important angle which we are interested in. You see, if we look at the original part of the ray, this is supposed to be the original part of the ray. The incident ray is expected to travel straight within the prism. So the broken line remains the original part of the incident ray. However, by virtue of the difference in densities of the two media, air and then the glass, its direction is bent from this direction to this direction. So we are interested in determining how much is the ray bent or deviated. Okay, so this angle between the angle of the refracted ray and then the original part of the ray, incident ray, becomes the angle of deviation, sigma. So we also have sigma representing angle of deviation. Now, when you look at the whole of this angle, and then the whole of this angle. Can we say they are equal? Can we say that this whole angle is equal to this? Class, can we say that? I want your views.
Yes.
What's
Yes.
on
Yes.
what reason? On what reason can we say that? On what reason?
Is vertically opposite.
Thank you. So because vertically opposite angles are equal, then I can be equated to R plus sigma. Therefore, sigma, which is the angle of deviation, can be determined by I minus R. So in refraction, angle of deviation is equal to when you subtract the angle of refraction from the angle of incidence. Please, is that clear? Under reflection of light, we learned that if there's a mirror and you incident light, that's the normal. When you incident light, there's the angle of incidence I. Because angle of incidence is always equal to angle of reflection. If there's I, this is also I. Now, if you want to, in mirrors, if you want to measure how much the part of the incident ray is deviated, you extend this line, and the angle between the original part and then the new part becomes the angle of deviation. So under mirrors, angle of deviation sigma is given by this whole angle is 180. So 180 minus 2 times R, 2 times I is the angle of deviation in mirror. So under mirrors, angle of deviation is given by this, whereas under refraction of light, angle of deviation is given by this. So take note of the two different relations for determining deviation. Please, is there any question? If you have any question, quickly ask. All right. You can be silent in my physics class. So, Amma, Elizi, you all know. So learn to talk. Okay. Now, we are interested in something. You see, we found the angle of deviation, sigma, I minus R. Now, this ray is expected to go straight. By virtue of difference in refractive indices, this is its new path. It is as if when we look at the original part of the incident ray and then the now part of the refracted ray, it is as if the ray has been moved horizontally. It's like going here and you've been pulled to come here. Okay. So we are interested in this distance, which is termed as. Luther, please mute yourself. Luther. Mute yourself. Whenever you want to talk, you then unmute, okay? So we are interested in this distance D. And this distance D is known as displacement. But we add an adjective, lateral displacement. The lateral displacement, D. We are interested in this. Okay. So how do we determine this lateral displacement? Let me name this point O. This is the point B, C, and then the point D. Of course, the thickness, the light incidented must go through this thickness. Okay, when incidented at this side. So we are assuming that the width of the prism is equal to H. H is AD. H is AD or BC. Okay. Now, when we look at whatever we have within, we have two right angle triangles. OD, then the hypotenuse, this is C. Then, so this is the point C. That is triangle ODC. Then we have another right angle triangle OBC. 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 This is also perpendicular to this. So these are the two right angle triangles we have in OBD. OD is equal to H. The angle at O, this is R, angle of refraction. This is angle of deviation, sigma. Okay. We are saying that let this lateral displacement be small letter d. So our concern is that we want to have an expression for d, a formula for determining d. Now, when we take the cosine of r, cos of r, we have OD, which is h, divided by the hypotenuse OC. Then, if we take sine of this, sine of the angle of deviation, sine sigma is equal to the opposite, which is d over OC. So we have equation 1, equation 2. Since we have OC in equation 1, OC in equation 2, let's make OC the subject in 1 and 2. So let me call somebody to help make OC the subject. Joel, from equation 1, help me make OC the subject. Joel, from equation 1, OC would be equal to, then Elizabeth, make from equation 2, make OC the subject. Joel, what have you had for OC in equation 1? Oh,
That please, H over cos R.
thank you. So H over cos R. Then Elizabeth, OC in equation 2.
Please, D over sine sigma.
D over sine sigma. Thank you. All right. So once we have OC in both, we equate. So it means that H over cos R is equal to D over sine sigma. Let's make D the subject from here. So Joel, D on this equation will be equal to D from this equation will be equal to, oh, time wasting. Okay, Frida or Elizabeth. Elizabeth,
D will be equal, D will be equal to H over cos R times sine sigma.
so H sine sigma on cos R. Okay, so this is how we can determine the lateral displacement D. Sigma is equal to I minus R divided by cos of R. So if we want to find how much is the original part of the ray deviated, this is the sign D. This is what we use. When you have H represent the thickness of the glass block, I is the angle of incidence, R is the angle of refraction. Okay, so knowing these quantities, you can easily find the lateral displacement D. Okay, you can easily find the lateral displacement D. Now, one other thing you have to understand in refraction in triangular prism is that you can determine the refractive index, the absolute refractive index of the glass block by applying Snell's law, the ratio of the sine of the angle of incidence to the sine of the angle of refraction. What this means is that if you are given the refractive index of the material, you can easily, and then you are given the angle of incidence, you can easily calculate for the angle of refraction. I'll create a question. Another thing you must understand is that for refraction of light in parallel, you see the side AB, the side AB is parallel to the side DC. Okay, so what it means is that for refraction of light along parallel planes, angle of incidence is equal to the angle of emergence. So I will be equal to E for refraction of light along parallel plane, meaning that, hey, Huawei hasn't muted. Huawei, please mute yourself. I'm getting, huge feedback here. All right. Thanks for muting yourself, Huawei. So, supposing I is 30 degrees, you must have E to be 30 degrees as well. And this is due to the fact that AB and DC are parallel lines. Okay. Let's create a question. Please, can I clean the board? Or you are still writing? Do I clean the board? So you'll be applying this in your practicals and the refraction of light in rectangular prism. You'll be applying this. So take note of this theory. I'm sure some of you have even treated that already. Okay, let's treat the theory. I'll look for the questions and then give it to you. Okay. Let me create a situation. In a rectangular prism, the refractive index of the prism is 1.5. And the angle of incidence I is equal to 30 degrees. Our work is calculate R, I we are to calculate the angle of deviation. And then we are to determine the lateral displacement D. So we have glass. We have glass, a glass block or prism. Its refractive index is 1.5. Light is incidented at an angle of 30 degrees. We are asked to calculate for the angle of refraction, II, angle of deviation, and III, the lateral displacement, small letter d. 5 minutes, quickly go through this. Let's see what you can produce. Within 5 minutes, give it a try. Let's see what you can do within the time. Then we all discuss it. I'm timing it. It's exactly 10:40. So at exactly 10:45, I'll come your Mamiya, what did you make for I? Angle of refraction R.
19.471
So
degrees.
let's see if that is right. So using Snell's law, the absolute refractive index N or mu must be sine of I on sine R. Okay. So if that is the case, then Cadmiel, your hand is up. Cadmiel. Okay. So the refractive index is 1.5. If 1.5, then sine of I is 30. 30 degrees over sine of R. So knowing the refractive index and then I, you can find that. So sine R, therefore, is equal to sine 30 degrees divided by 1.5. And sine 30 is 0.5. So 0.5 divided by 1.5. And what's the ratio? 0.5 divided by 1.5. Is it 0.75? Mamiya and Co. Give me response. Frida, Angel, then the gentleman. What's the ratio? 0.5 divided by 1.5.
So please, it's 0.3 for Karen.
Okay. Therefore, R is equal to the sine inverse of 0.333 recurring. And what's the sine inverse of that? R is equal to sine inverse of that.
19.451.
Okay, so approximately 19.5. 19.5. So this will be the angle of refraction. Let me see by hands those of you who got this correct. Raise up your hand if you got it. One hand, Angel, Elizabeth. All right. Okay. I'm seeing more hands. I'm seeing 7 hands out of 20 something hands. So, okay. Then the angle of deviation. The angle of deviation. Angle of deviation, sigma is equal to I minus R. And the refraction of light, or under refraction, deviation is given by this. So this is equal to 30 minus 19.5, which is which is 30 minus 19.5.
10.55.
Okay. So that is it with the deviation. Then the lateral displacement. Please, how many of you also got this? The angle of deviation. Show by hands. 2, 3, 4, 5. Okay. 7 hands. Okay, 9. All right, thank you. Then let's look at the deviation. The deviation. The lateral displacement, D. So from the equation we derived, the lateral displacement D is given by H times sine of the angle of deviation divided by sine of R. Sorry, cos of R. Please, over here, do not make the mistake to say that this is tan. Do not make the mistake to say that this side is equal to tan. Why can't we say that? Though it is sine over cos, but why can't we express that as tan? Anybody? Anybody with a tangible reason as to why this cannot be tan? Yes, Luther, is your hand up? Martin Luther King, is your hand up? Elizabeth, are you there?
Yes, please.
Why can't we say that this sine sigma over cos R is equal to tan? Why?
Please, I have no idea.
But are you aware that tan sine over cos is equal to tan?
No, please.
Okay, then you are forgiven. Luther, is your hand up? Yay.
The sine theta over cos theta is equal to tan theta.
So why can't we say that sine sigma over cos R is equal to tan?
So the sigma and the R are not the same.
Exactly. Thank you. You see, it's because these two angles are not the same. If we had sine sigma over cos sigma, hooray, it is equal to tan sigma. If we had sine R over cos R, tan R, but here the angles are not the same, so we can't make that conclusion. So not every sine divided by cos is a tan. You need to look at the angle. Okay, so DH is 2 centimeters. So 2 times sine of the deviation, we got 10.5 divided by cos of R. R is 19.5. Therefore, calculate D for me. Or what did you make for D? Generally.
0.388.
388 centimeters. So that's the lateral displacement or the lateral shift. Then IV, we have to calculate for the angle of emergence E. Mamiya, what did you make for E?
I still haven't figured an equation for the E.
Oh, Elizabeth, what did you make for E? Luther, what did you make? Kelvin, Cadmium.
says
Step is 30.
Mamia, E is 30. As said by them. Because I said refraction of light along parallel plane. Because AB and DC are parallel lines, angle of incidence will be equal to the angle of emergence. So there is 30 because this is parallel to this. Are you okay?
Yes, please.
All right. So take note of this theory. You'll be doing it in practicals. During practical session, what you do is that you trace the outline of the glass prism, then put 2 pins here, P1, P2. Then you look through, you trace the image of these 2 pins by looking through the other side, the other parallel side. So you go through that in practicals. All right, let's move on and then look at the concept of real depth and apparent depth. I'll send you another question on this as your assignment so that you can be assigned to something. The concept of real depth and apparent depth. You see, during sunny afternoon or during sunny afternoon, whenever you visit the pool, river, lake, okay, stream, then you look at objects within the water body. It always looks as if the water is just shallow. So when we were growing up, we visit the river and then try to catch fish with our hands. By looking through, you see fishes within. But when you try push your hand in to catch one of it, you can hardly do so. Yeah, this is because as you look through the water, that position of the fish you are seeing is a virtual situation. It is not real. So what you see is just an image. So when you push your hand to that level, because the fish ideally isn't located at that spot, you can hardly catch it. Okay, so when you look at fishes in rivers and aquarium, the apparent view of fishes in S has something to do with refraction of light. 2, when you fill buckets with water and then you drop a coin under it, you always and then you look through the buckets or the base to just have a view of the spot. You always realize that the spot or the base of the bucket looks shallow. Okay, whatever you see is as a result of optical illusion due to refraction. It isn't shallow, but it is because of something. When you place a glass block, this rectangular glass block thing, when you place it, okay, you place a coin under this and you view the coin through the glass. You always see as if, okay, the glass or the coin has been pushed forward. That is the concept of apparent view and then the real view due to refraction of light. So let's pick this to be water in a cup or water in a basin. an object is placed beneath the basin and an observer above, this is water. So this is the meniscus of water. So this is the object placed below. Now, an observer who wants to have a view of the object above, how does he or she see the object placed below? Now, under refraction, whenever light travels, you see, for an observer to see this, light must come from the object. Okay, we see as a result of reflection. So light from the object is picked by your eyes, and then your brain does the interpretation. Okay, so we see as a result of reflection and refraction of light. So for the object, for the observer here to see, light must come from the object below. But when the light from the object goes perpendicularly to the surface, it goes undeviated. Okay, so this is one ray of light. Whenever light goes at an angle, so this is another ray coming from the object. This is angle of incidence, I. But because this light is moving from water to air, it will bend away from the normal. So this becomes the refracted ray, which is bending away from the normal. When we extend or extrapolate this line or ray, we have this. Okay. Now an image will be formed when two refracted rays actually meet or appear to meet. This refracted ray and this are appearing to meet here. So the object which is over here, its apparent position will be here. So this is the image of this object O. All that I'm saying is that an observer looking through to see this object would see the object as if it is here. So this is similar to a fish over here and an observer looking at the fish from above, okay, would see the fish to be here. So when you stretch forth your hand to catch it, it is actually here, but you are being deceived to be here. So there's no way you can catch the fish, okay? Now the distance from the water surface to the position of the object is known as the real depth, RD. So R subscript D is equal to the real depth. The distance of the image from the surface to where the image is known as the apparent depth. Apparent depth. And we can use this situation of real depth and apparent depth to calculate for the refractive index of the liquid. Please, if there is any question, quickly ask before I continue. If you have any question to ask.
Sir, please, where is the apparent depth?
Pardon?
Please, where is the apparent depth located in the diagram?
So the apparent depth the real depth and apparent depth is measured from the surface of the liquid. So this distance from the surface to where the object is the real depth. The real depth of the object. Then this distance from the surface to where the image is. That image you are seeing is the apparent depth. Are you okay?
Yes, please.
All right. So this is angle of incidence I. This is also angle of refraction R. Now, by corresponding angle rule, this angle is equal to this angle. They correspond. So if this is R, this will also be R. Let's label this as O, B, C, D. The points. Let me redraw this. The incident ray is here. Then we have this one. O is here, the object. D is this point. Then a ray coming from D this is the image I. And we are calling this to be a point B. Okay. So if that's the point B, then this is R. If there's a normal, this is a refracted ray, this is R. This is I. By vertically corresponding angle rule, this angle is equal to this angle. So this is also R. So we have C, D, O. Okay. Now, refractive index of a material, the liquid, will be determined by sine of I over sine of R. Okay. So from what we have, if you want to determine the refractive index as the light moves from water to air, the observer is here. It's in air, but the light must come from the object below. So the light must move from water to air. So if we decide the refractive index, it will be refractive index as light moves from water to air. And this is equal to sine of the angle of incidence I to the sine of the angle of refraction R. But the problem is that whatever we have here is not absolute. We are looking for absolute situation. And the absolute situation must be from air to water. So if I have the refractive index from water to air to be equal to sine I over sine R, what will that be if we are considering the absolute situation? Yes, any idea? How would this change if we want from air to water, not from water to air? Any idea here? Yes, Mami, yeah.
Sine of R over sine of I.
Thank you. So this will be sine of the inverse. We went through that. So sine R over sine I. Okay. Now, from our diagram, let's determine sine I. and sine r. From the diagram we have here, what will be sine I? Can somebody help? What will be sine I from our diagram? This is the angle of incidence, angle of refraction. So what will be sine I? Yes. Calvin, Cadmiel, Mami Ya, Elizabeth, Frida, Mr. Annan. Yes. What will be an expression for sine I? Here. You are getting lost. If you consider the right angle triangle OCD, can't you determine sine I? Considering the right angle, Camille, go ahead. Camille, go ahead. Oh. Camille, your hand is up. I said go ahead. Okay, maybe he's not hearing me. So when you consider triangle OCD, sine I is the opposite CD over the hypotenuse OD. So when you consider OCD, sine of I is equal to the opposite CD over the hypotenuse. What about sine R? Yes, I want somebody to help me with sine R. Yes, Elizabeth.
CD over BD. CD over BD.
Exactly, CD over BD. So CD over BD. Okay, now under what we call as normal incidence. Normal incidence means that we are considering very small angle of incidence. Okay, we are considering very small angle of incidence. When you consider very small angle of incidence, you equally have very small angle of refraction. So the condition for this is that we consider at normal incidence, at normal incidence. And normal incidence means that we are considering very small angle of incidence. So this I value is very, very small. If I is very, very small, then R would also be very, very small. Okay. So at normal incidence, you get sine I being equal to tan I. And sine R also being equal to tan R. So we've had sine I. I want you to also help me find tan I. What will be tan I from our diagram? Yes. Tan I. Yes, who is answering for tan I? Elizabeth.
Please, CD over OC.
So tan I, opposite over adjacent. Okay. So CD over OC. So CD over OC is tan I. What about tan R? What about tan of R? What about tan of R? Elizabeth again.
CD over BC.
CD over BC. CD over BC. So if we have this, then let's find the refractive index of the material. We are saying that the absolute refractive index, which is sine R over sine I will be equal to, what is sine R? Sine R is equal to tan R. So either we use this or this. Let's use tan R. So we have CD over BC divided by sine I, okay, which is also equal to tan I. So CD over OC. Let's simplify this. Let's simplify this. This will be equal to CD over BC times OC over CD. This and this will cancel out. So we have the absolute refractive index giving us OC over BC. From the diagram, what is OC? Yes, class, from the diagram, what is OC? What is OC?
Real debt.
So since OC is the real debt, this is equal to real debt RD over BC. BC is the apparent debt. BC is the apparent debt. So we are using this concept of the actual debt divided by the apparent debt to determine the refractive index of the liquid. So when an object is placed in a liquid and the image is seen as a result of refraction, the image is formed somewhere, we can use the concept of its real debt over its apparent debt to calculate for the refractive index of the material. So this ratio would give us the refractive index if the object is placed in water, the refractive index of the water. If the object is placed under a glass block, we can also calculate for. Now, what's up? If we have RD, look at something. OC is the real debt. CB is the apparent debt. What about this distance? What about this distance? So the object originally is here. An observer looking above sees this object to be here. It means that this object, which is originally here, seems to be pushed up. It has been moved up. So we call this distance as a vertical displacement. Vertical because it has been moved vertically. It appears to be moved vertically. So we call this distance the vertical displacement. So from what we have, we could see that OC is equal to OB plus BC. So OB, which is OC minus BC, this is equal to OB is equal to the vertical displacement of the object. So if we are asked to calculate for the displacement or vertical displacement, is the difference between the real depth and the apparent depth. Please, is that understood? If you have any question, you can also ask. So I explain further. Any question? Let's play around this. Let's play around this. The vertical displacement D is given by real depth R minus apparent depth. Then we've also noticed that the refractive index is equal to real depth over apparent depth, right? So when we make let's make A the subject from here, or even R. R being made as the subject from here is equal to the refractive index times the apparent depth. So if we substitute this into this equation, we have the displacement D giving us the absolute refractive index times A minus A. So that A out, we can have the absolute refractive index minus 1. This can be one simple equation to determine the displacement. So if you have the apparent depth, when you subtract 1 from the absolute refractive index, the product will give you this. Or even though these relations are not so much important because it's just a subtraction, or we are just playing around it, or from the same relation D, which is equal to R minus A, if we make A the subject from here, A is equal to R over the absolute refractive index. Come and substitute this into the equation, and you have the vertical displacement to be equal to R minus R over the refractive index. When you pull out R, you have 1 minus 1 over the absolute refractive index of that. So these are different ways to calculate for the vertical displacement D. Okay. Please, is that okay? So this is the whole concept of real depth and then apparent depth. We can use the concept of real depth, apparent depth to find the refractive index. Then we can also determine the vertical displacement or vertical shift of the objects. Okay. And this is happening due to refraction of light. Now, an application of this. Do I clean the board? Mami Owusu, Mami Ya, Elizabeth Frida, Kelvin, Lenko. Do I clean the board?
Sir.
Hello.
Sir, please, can you move the camera to the down? I want to see something.
Is it better?
Thank you, sir.
Okay. Are you done? Can we continue?
Yes, please.
Yes, sir.
These days, you teach a concept, you need to connect it to application, because our questions are more of application than just the theory. Calculate the refractive index. If the real depth is this and the apparent depth is this, oh, this is just straightforward. These days, we don't ask much of those questions, but questions that would elicit critical thinking. So an application of this is that we have three liquids, three immiscible liquids. Three immiscible liquids. Mu1 is the refractive index of the first one. Mu1 is the refractive index of the first one. Its depth is equal to D1. We have another liquid of refractive index mu2. Its depth is D2. And then lastly, we have this liquid whose refractive index is mu3. The depth is D3. Now an object is placed below, an object is placed here. The question is that determine the total apparent depth. Okay, so the object is here. They are liquids. An observer is here looking at the objects down there. And you are asked to calculate for the total apparent depth as the observer views the object through the three liquids of different refractive indices. Then you are also asked to calculate for the displacement. So determine D apparent, and then also determine total displacement of the objects. This is a true application question. So let's see how to apply whatever we've learned to tackle each of the situation.
That's right.
For liquid one, now, before we go through the liquid, you see, this concept works on this when the absolute refractive index of 3 is greater than the refractive index of 2, is greater than the refractive index of 1, or the refractive index of 1 must be less than the refractive index of 2, and that of 2 must also be less than the refractive index of 3. So look at the order. Out of the 3 liquids, which one is the densest of all the 3? Which liquid is the densest among all the 3 liquids? Hello. Look at the order. Out of the 3 liquids, which one is the heaviest or the densest liquid? Hello.
D3.
It's 3. So the third one. So it means that for this to work, the liquids must be in a form of either increasing refractive indices when we are going down or decreasing refractive indices when we are going up. Meaning that you can't just mix the liquid anyhow for it to work. Okay, the condition works on either increasing refractive indices of the 3 liquids or decreasing refractive indices. So it works on this condition. Okay, so for liquid 1, liquid mu1, we just saw that absolute refractive index is given by real depth divided by apparent depth. So we are calculating for the total apparent depth. So AP or A subscript D will be equal to the real depth over the refractive index. So for liquid 1, the apparent depth will be equal to the real depth is D1 divided by the absolute refractive index mu1. Liquid 2, for mu2, the same thing. The apparent depth would be D2 over mu2. D2 over mu2. Then lastly, for liquid 3, its apparent depth will be equal to D3 divided by the absolute refractive index mu3. Therefore, total apparent depth will be equal to the summation of all the apparent depth in each situation. So D1 over mu1 plus D2 over mu2 plus D3 over mu3. This will be the total apparent depth. I want you to think through and help me out with II. What will be the total displacement? Think through it, and then I'll invite one of you to share your answers with me. What will be the total? If there's the total apparent depth, what will be the total displacement? Anybody? Anybody to help us? Yes, Maria.
Please, I don't understand why the total, the DAP, was it yeah, I don't know why the AD, I
Apparent
don't know.
apparent displacement. AD. Uh-huh.
Okay,
So let me write it well.
I understand.
Let me write it well for all. This is total apparent displacement. Mamia, because of you, the marker will not write. So the total apparent displacement is the displacement d1 in first medium mu1 plus d2 plus d3 on mu3. So what is the total displacement? What is the total displacement? If this is the total apparent depth, instead of displacement, it will confuse you. So let me write this as total apparent depth of all of them, okay, is this. What then will be the total displacement? Total displacement, or let me, instead of total, let me use the displacement. Yes. What will be the displacement? Yes. Who is ready to share whatever you had with us? How do we determine the displacement? If it is just one liquid, okay, just one liquid, the displacement is equal to the real depth minus the apparent depth. If it's one liquid, the displacement is the real depth minus the apparent depth. This time we have 3 liquids. So what do you think will be the displacement? An expression for the displacement. Joel, help us with the displacement. How do we determine the displacement? Joel, Luther, Jonathan, Kelvin, Weku, Chireme, Michelle, Mr. Anna. Yes, how do we determine the displacement? Okay, Mamia, tell us what you think. Mamia, share with us what you think.
I think it will be the total apparent displacement minus the total real displacement.
Mamia, when we went through the drawing, the real depth is always greater than the apparent depth. Okay. Okay, so let me fine tune what you said. So the displacement will be equal to still real depth minus the total apparent depth. But what is the real depth? The real depth is for each one d1 plus d2 plus d3. So the total real depth will be d1 plus d2 plus d3. So d1 plus d2 plus d3 is the will be the total real depth minus whatever we have as the total apparent depth. Total apparent depth, which is this. Okay, which is this. So whatever you get for this plus this is the total apparent depth. So when you subtract it from the sum of the actual depth of the three liquids, it gives you the displacement. Please, are we okay? Hello, are we okay?
Yes, please.
So all that we've done is that we are using the concept of refractive index being real depth RD over AD. So pick for each of the liquids, determine AD, the apparent depth, which is the real depth over the absolute refractive index. So for this one, you have D1 over mu1. For the second liquid, you have D2 over mu2. For the third liquid, you have D3 over mu3. These are the individual apparent depth of each one of the liquids. Okay, so you determine the total apparent depth by adding all of them. That's what we've done here. Therefore, if you are looking for the displacement is always real depth minus the apparent depth. And since these are together, what is the total real depth? D1 plus D2 plus D3. Then the total apparent depth is whatever you've calculated here. I have a question on this which dropped in Nigeria last year Nigerian physics paper under this. Okay, I'll look for it and then as part of your assignments, give it to you to try your hands on. Okay, this is a real application of whatever we've done. Please, is there any question? Is there any question? All right. Let's do something. We have about 10 minutes, or 18 minutes to go. But let's start discussing something on triangular prism. This is the triangular prism. Okay. Now, the triangular prism is identified by a special angle. So, if you want to buy this, you buy this using the angle of the prism or the refraction angle. This is such that the angle of the prism is 60. We have others whose angle of prism 30 degrees, 45 degrees, and even 90. So if you are going to buy this, you use the angles. Now, these are done with glass. This is glass, and then plastic. We have these ones, which is also made of plastic. So you buy triangular prism with the refraction angle and then the nature of the material, whether you want plastic one or glass. Now, how different is this from rectangular prisms? The shape of this one is a triangle. Okay, it's a triangle. Once you place it like this becomes the base. So A, B, C. BC is the base. And this is the angle A, angle of the prism. So A is equal to the angle of the prism, or refracting angle. The refracting angle. So either you call A as the angle of the prism or the refraction angle. We'll be using it. Now, the triangular prism has two refracting planes. There are two refracting planes. That is AB, and AC. Okay. So a triangular prism has two refracting planes, this side and this side. Meaning that when you incident light at one end, it will go through double deviation, unlike this one. This one, when you incident light at one end, it will deviate, and whatever happens here is equal to what is here. Okay, because this side and this side are parallel. For a triangular prism, when you incident light at one end, it will deviate at this side, and when it is coming out from the other end, it will also deviate. So light goes through double deviation in triangular prisms. Okay, so because triangular prism has two refracting planes, light undergoes double refraction. Light goes through double refraction in triangular prisms, whereas in rectangular prisms, light goes through only one deviation. Please, are you with me? Hello, class, are you there?
Yes, please.
So the features here are that we have the refraction angle of the prism, which is peculiar for different prisms. Like a triangular prism has also double, there are two refracting planes, this and this. Okay, so when you incident light at one end, light will bend and when it is coming out of the prism, it would also bend again. But please, here, angle of incidence is not equal to angle of emergence. It only occurs on some conditions which we'll discuss. But ordinarily, for triangular prism, angle of incidence I is not equal to angle of emergence E. Now, the special characteristic this one has is that because light goes through double deviation at AC and AB, triangular prism has the ability to add the two deviations to form a larger deviation. Okay, so because light goes through double deviation, it has the advantage of adding the two deviations to form a larger deviation. So the deviation of light which occurs at AC and AB is added to form a larger deviation. And it is because of this unique attribute of triangular prism, the reason for which triangular prism is used for dispersion of light. For this reason, the triangular prism is used for the dispersion of light. Class, what is dispersion of light?
Yes, carry 10 minutes.
I can't wait. The bus driver is coming. I have to go and
Admiral,
Cadmium.
are you answering my question? What is dispersion of light? Yes. Anybody? What do we mean by dispersion of light? You are saying that the triangular prism is used for the dispersion of light. What is dispersion of light? Elizabeth,
This is the separation of white light into its component colors when it passes through a glass prism.
exactly. So separation of white light into its component colors when it passes through glass prism. But here, specifically triangular glass prism. So when you incident white light at one end here, this is white light. Light will deviate this is A, B, C. Light will go through deviation here. And when it is coming out of the prism, it will also go through deviation. Now, when we trace the original path, the white light that is incidented is spread over this range. It's spread over this range: red, orange, yellow, green, blue, indigo, violet. And it could do this because it has the ability to add refraction here and then refraction at the other end. So it is of this reason for which the triangular prism is used for the dispersion of light. Okay, so we'll go into it deeper tomorrow. If you have any question, ask. Is there any question? Mamiya, Frida, Luther, I think I must know, or Mr. Anand. All right, so if there is no question, then this is where we draw the curtains on today's meeting. We'll continue tomorrow exactly at 12, okay? Okay, if you have any question,
Okay. Yes, sir.
forward it,
Yeah.
WhatsApp it to me. Is there any question?
Yes, sir.
All right. Then until tomorrow, in fact, bye-bye. I'll post your videos, the video. I'll send it to the group so you can have access. All right. Bye-bye.
Yes, sir. Bye-bye.
All right. Yeah.